Okay, so welcome everyone to the second half of our discussion on independent set of disks. So to summarize what happened in the last lecture, uh, what we showed was if we have this collection of disks, then we define what's called the less than or equal to k level of those disks. And we proved this statement that the less than or equal to k level of D will have at most n times k vertices. And what are vertices? Just to recall, so if you look at the figure in blue here, if you look at the intersection of any two disks, the boundaries of those two disks will intersect at 2 points, right? So the black points that I've drawn are actually vertices, right? So how many of them will have depth less than or equal to k was the question, and we proved that it is at most n times k such vertices. Okay, so we'll need this fact going forward. That's why I've written it there. So we'll continue with these theorems and lemmas we are proving, and eventually the goal is to design an efficient approximation algorithm to compute the independent set of disks. Okay, so to get things started, so we have to define what's called a geometric intersection graph. Okay, so what is that? Pretty simple. So given a collection of disks D, its corresponding geometry intersection graph is the following. So think of each disk as a vertex, right? So if you look at the blue figure on the right, what we have done is, so in the example, we have 4 disks here. So each disk will correspond to a vertex in the graph. So that's why we have 4 vertices. And when will we put an edge between 2 vertices? Because it's an intersection graph, we'll put an edge between 2 vertices only when these disks intersect. So that's why you'll see an intersection between A and B, but you won't see an edge between A and D because the disks A and D don't intersect. So very simple. So one thing is the notation might get, it shouldn't, from the context, it should be very clear that when we say vertices in the geometric context, we mean these black points here formed by the intersection of the vertices. But in the graph world, when we say a vertex, it's just a vertex corresponding to a disk. Right? So that should be clear from the context. Okay. So now, so this theorem that I've written here, we need a special case of this. So I'll write down a corollary, which is a special case of this theorem, which is what we need going forward. So assume that the maximum depth in our collection of disks is k, right? So then it's easy to see that the total number of vertices in our disk is order of nk, right? It's just a special case of this theorem, right? Because the max depth itself is k, you cannot have more than nk vertices in your collection of disks, right? So let me write that down and then translate to what that means in the geometric intersection graph setting. Corollary 1 for n disks with max depth. I hope everyone remembers what max depth is. It will be that point in the plane which is being covered by the maximum number of disks, which is at most k in this case. The total number of vertices, so when I say vertices, this is in the geometric context. Vertices will be order of nk, right? So now, what does this imply in the job? So this implies that the corresponding intersection graph has order of nk edges. So this should be easy to see, right? Because still, let me be sure everyone gets this. So we are saying the number of such black vertices are order of n of k. And now every edge, and these, because these blue disks intersect, they contribute to, there'll actually be an edge in the corresponding geometric intersection graph, right? So every edge in the geometric intersection graph corresponds to at most two intersection points. It's two vertices in the intersection, right? So that basically implies that there cannot be more than order of n k edges in the corresponding intersection graph. So what we crucially need is the following fact. Crucially, what this implies is there exists a vertex in the graph, in the intersection graph, with degree order of k, right? Because the number of edges is order of n of nk. Clearly, there has to exist a vertex with degree order of k, right? Very easy to see. Okay, good. So now we have to remember this fact. Let's keep this in mind and let's go forward. Now, let me call this a lemma and not a theorem. Okay, so now I'll state a lemma which is true not just for geometric intersection graphs, but for general graphs. So let me write down the statement. It's a simple lemma, but a graph with n possibly weighted vertices if the following property holds: if every subgraph basically means the graph defined on a subset of the vertices, has a vertex with degree less than or equal to delta. It means you pick any subgraph in this graph, there'll always exist a vertex with degree less than or equal to delta. Then we can make the following claims. Then there exists an independent set of size at least n over delta plus 1, or if you're looking at the weighted version, or weight w over delta plus 1, where w is the total weight of the vertices. Okay, so let's quickly prove this. So in the unweighted setting is very simple. I'm sure many of you must have seen this. Simple greedy algorithm. What's the algorithm? Just pick the vertex with the smallest degree and put it in your solution and remove that vertex and all its neighbors from the graph and just repeat this process. Right? So yeah, let me just write that down. Pick the vertex V with the smallest degree into the solution, and then remove V and its neighbors from the graph. Repeat till graph is empty. So you must have seen this before. The analysis is very simple. I'll not do it. So I'll leave that as an exercise. That this will actually give you a size of independent set via this process will be at least n over delta plus 1. Okay, so slightly more interesting case is the weighted case. Oh, by the way, might be a good exercise to understand that this algorithm will not actually work for the weighted case, right? So you should try to figure that out. Show an example. As to why it fails in the weighted case. Yeah, it's a simple exercise, but we'll kind of be able to appreciate the next algorithm that's coming for the weighted case. Okay, so let's look at the weighted case now. So the high level idea is the following. You color the graph. I hope everyone knows what coloring is. Color the graph with delta plus 1 colors and pick the color class with largest weight. Right, so if you can actually color this graph with delta plus 1 colors, then you can see that if you pick the color class with the largest weight, so this will have at least W over delta plus 1 weight. And because they all have the same color, they have to be an independent set. Right, so this will be guaranteed. But the question is, how do you actually color them? Right? So what's the coloring algorithm? So it's again greedy. So what we do is pick vertex V with degree less than or equal to delta. So we are guaranteed the existence of such a vertex. So you remove V from the graph and recursively color the graph. So whatever is remaining, so you remove the vertex V and of course all the edges corresponding to it. So now you recursively color the graph. Right? So now the crucial thing is we can recursively color the graph because what have we said in this lemma statement that every subgraph will always have a vertex with degree less than or equal to delta. Right? Because we have that strong property, we can actually recursively color the graph because that property will still hold on the remaining graph. Okay, good. So now once the recursive coloring comes back to us, what we do is we put V back. Now everyone else in the graph is colored, only V has to be colored. So how do we choose its color? Well, we put it back with color in 1, 2, so on up to delta plus 1. So these are the options we have, right? From 1, 2 up to delta plus 1. Now it has to pick a color from this with a color this, which is different from its neighbors. Neighboring colors. Right, because its degree is less than or equal to delta, all its neighbors must have at most picked delta colors from this palette of delta plus 1 colors that we have. So there will be at least one color which we can, which V, the vertex V can happily pick and create no conflict. Right, that's it. So we have actually proven this lemma now. Okay. So then, if you remember in the last, so now we have proven this corollary 1, we have proven this lemma 1. And let me state what the main goal of the last lecture was. Right. So there was one theorem which we wanted to prove, which we are now ready to prove. This is from the previous lecture. And let me just state that here. Given n possibly weighted disks into D of total weight W and max depth less than or equal to K, one can find an independent set of size n over K. This is in the unweighted setting, or weight W over K, the weighted set, right? So now we have proven everything that is needed to show this theorem. Actually directly follows from what we have, all the things we have proven till now. Right? So this kind of is obvious, but then I'll just prove it anyways. Okay, so just have to combine corollary 1 and lemma 1. Right, so pick any subset of disks by corollary 1 there exists a vertex in the intersection graph with degree order of K. Right, so that corollary was true for any subset of this. Right, not. So then, this is exactly the property which we need in our lemma 1, which is what we have proven just now. It just needs this property that any subgraph has degree less than or equal to delta. And that actually is what is exactly guaranteed by our corollary. Right? That there always exists a vertex with this property. Right? Therefore, we can apply lemma 1 on the set of this with delta set to lemma 1 has a parameter delta, so we can set it to some order of k, and that's it. So once you do that, then you will get an independent set of size at least n over k or weight w over k. That's it. Right, so this was an important theorem that we need. But this theorem by itself is not, doesn't guarantee a large independent set because, right, because it could happen that, let me just draw a lot of disks here. So depth is very large here, right? So then because depth is large, well, just applying this theorem might not, will not give us a large independent set, or it will not guarantee a large independent set, right? So, oh, okay. Whereas, just a second, yeah. So, whereas it could actually happen that we actually have a large depth, just like the previous case, but maybe there is a large independent set waiting here, right? The ones I've shown in green. But this theorem will say that, okay, depth is very large, so I'm sorry, I cannot promise you a large independent set, right? So it cannot differentiate really between these two, different inputs where the independent sets are very different, right? So here is where linear programming will be very useful now, right? So what we'll actually do is we'll actually create a multi-set, right? So LPs will be useful here. This will help us out. We'll create a multi-set. By that we mean the same disk could get copied multiple number of times, right? So you'll see that. And what will happen is that now on this new multi-set, relatively the max depth will be very small, right? Well, I mean relative to the size of the largest independent set, relative to that, the depth will be small. And that's exactly what, and then if you apply theorem 1, then it can guarantee you a large independent set, right? Relative to the largest independent set, the depth will then be small. So then you can happily apply theorem 1, right? So essentially what LPs help us do is, so if you look at this example, right, this is really intuition, right? So all these red disks, right, they're not very useful, right, in contributing to a large independent set. It's the green ones who should really stand out. And LPs exactly help us do that. So they'll assign very small weights to these red disks, but they'll assign large weights to these green disks, right? So if we are very careful about the weights and our rounding algorithm takes care of those weights, then we'll create a multi-set where these green disks will prominently show up and the red ones won't. And so on that new data set, when we apply this theorem 1, we'll be in a Good shape. Okay, so time for a linear programming formulation. So as always, we'll first write an integer program. And because integer programs can't be solved in polynomial time, as you know, NP hard, same story. So we have to convert it into an integer program. Sorry, a linear program. Okay, so then saying maximize. So we'll assign a variable xi with each disk, right? Which is basically 0 if it's not picked, and it's 1 if it's actually picked in a solution, such that, well, we write down the constraint. So what does this mean? It's basically saying the independent set condition, right? So for any point in the plane, the number of disks which can cover it is at most 1, right? So that's what independent set basically means, right? So that's, and this is the constraint we wrote in a couple of lectures back when we dealt with intervals as well. So nothing new. So but one thing is, so I'm saying for all points pj, right, in the two-dimensional plane, which could actually be infinite in number, right? But so you can't, but you can't write infinite number of constraints here. But the crucial thing to notice here is that if you say, look at this region, right, which I've shaded here, for all the points in the shaded region, they have the same equation. The same constraint holds true for all of them because the disks covering them are the same. Right? So similarly, if you look at this region, the red region, for any point there, the disks covering them are the same. So you can write just one equation per region, right? So essentially, the number of such regions are only polynomial, so should not be an issue. Only polynomial number of inequalities will be there, constraints. So that won't be an issue, right? So it's easy to see. And then we'll set xi to be either 0 or 1. But then as we know that that's the integer programming formulation. So we can't do that. So we relax that condition and we say, okay, take any value in between 0 and 1, in the interval 0 to 1. Right? Okay. So now let's, for this, so let's call the value returned by this linear programming formulation as opt of LP, right? So the claim is that opt of LP will be greater than or equal to opt. So this opt is the optimal solution for our original problem, the integer programming formulation. Right? So we took our independent set problem, formulated it as an integer programming problem. Right? So that will have some optimal solution, which is what we are looking for, but of course we can't compute it. So then we relax this condition of xi. So now, yeah, because xi can take fractional values, it could turn out that you could put in those fractional values and increase the value of this objective function. That's why we say opt of LP is at least greater than or equal to opt. It could be equal to opt, or it could be strictly greater than opt. Okay. So now we are ready to ready for the rounding algorithm, and that's actually very simple now, not very difficult. So originally this was due to Chan and Harpellet. But what we show here is actually a simplification of their rounding algorithm. So the idea is simple. Create, as I said, a multiset, right? So create a multiset D prime where disk I gets a ceiling kxi. So the linear programming formulation will assign some xi value to this disk. So then you create this many number of copies for this disk I, where k is a sufficiently large constant, large value, not a constant, but a large enough value of k, right? So this k you can determine later, but that's it, right? So let's do some calculations, simple calculations. So now what's the total weight of all the disks in this D prime? It's 1 equal to n. So each disk has a weight wi, its copies have kxi, right? And this is nothing but 212n wi xi. Now what is this quantity? This wi summation of wi xi, it's nothing but our opt of LP, right? You see here, right? This equation here where we say opt of LP is equal to max of this summation of wi xi, right? So now, and we also know that this is at least k times opt, right? So what this basically says is, this collection is nice actually, because now we have collected, the weight that we have collected is actually is large, and it has this term opt in it, which is good. It's basically it's proportional to the optimal value that we're looking for. So that's a very good sign. Okay, so what's the next thing you have to prove? Next thing you have to prove is about the depth, or the max depth, right? So for all points P, depth of P in D prime, right? What will that be? Well, just write it down. Summation over disk I containing P right? So you just basically look at all the disks which are covering this point P, and you know it's this many number of disks. Okay, so then doing some simple inequalities, we end up with this. We say this is k of xi, and this I'll just loosely upper bound with n. Summation of 1, I'll just loosely upper bound it by n. And now, what is this? This I containing P, right? So this is exactly the constraint that we had written, right? So the constraint that we have written here, that it should be less than or equal to 1, right? So it has to be satisfied. Oh, sorry. This was the previous lecture. Yeah, so this has to be satisfied. So this will be K plus M, right? Okay, so now I'm saying on this you can apply theorem 1, right? So this theorem 1 that we were talking about, now we are in a good situation to apply it. Let me do it here itself so that you can see everything in one place. By theorem 1, we get an independent set weight at least. So what was the total weight? Total weight was K times opt. And what was the max depth? We said the depth was always bounded by K by N. And now the claim is that this will be at least opt if you choose a sufficiently large value of N. So then the kind of the numerator and the denominator kind of absorb each other. Yeah, and we're done, right? So can you see that now theorem 1 is claiming that you'll find an independent set whose weight is some opt over some constant, right? And hence this implies an approximation factor of order of 1, right? So that was a beauty of using the LP, and it made sure that you placed emphasis on the right disks, right? And so it assigned. So what did it do, right? So when we said we created this capital K times xi copies, right? So if a disk is important, it should really be in the independent set. The linear programming assigned a higher xi value to it, right? So then more copies of those will be were created in this D prime. Because of that, now we could apply theorem 1 nicely and get a large independent set. Okay, good. So we are done. So we finally reached our constant factor approximation. So one final remark I should make is, if I can go to the next page. If the union complexity of your objects, here we looked at this, right? In general, the union complexity of your objects is n times alpha times n. In our case, alpha n was 1 for disks. Then you can use the same technique that we used today and get an approximation factor of alpha n. That's not very difficult to see if you just go through the things again. Okay, good. So did I have anything else to add? No. So in summary, we looked at the combinatorial properties of disks and came up with this nice theorem saying that the depth is small, then you can extract a large independent set. But we could not directly guarantee that our collection would have small depth. So then we had to use this linear programming formulation to create a situation where the depth will actually be small. And then we could extract a good independent set, a large independent set. Okay, good. So that concludes our discussion about independent set of disks. Thanks for listening. See you.